So this first sheet is just about a little bit of notation here. Just to remind you that as we take a look at these types of problems, you'll see the points represented in lots of different ways. Sometimes we'll actually write it out here as x comma f of x. You'll also see it sometimes written as x comma, and then they'll actually plug the equation in there, like the expression of what f of x equals. And so just be aware that you're going to have to be flexible with all of those because they all mean the same thing. It's x comma whatever we get out when we plug that x into it. That's all it's saying. Now we're going to be using that today as we continue through looking at some things like this. Again, a little bit of notation here at the start. I'm asking you to find m sub pq. And so that's m, we say sub, meaning it's a subscript, and then the subscript here is pq. Basically, this is saying find m at pq. Well, what does m normally represent? Slope. And so specifically what this is talking about is saying find the slope of the line that is passing through points P and Q. And you're going to see that kind of notation come up along the way as well. So to find m sub PQ here, we're just finding the slope between those 2 points. And notice the 2 points in this case are given on the graph. Okay, well, what would the slope be going between P and Q? 2. Yep. Because it's going up 8 over 4, therefore 8 over 4 equals 2. Great. All right, so now with that in mind, put all those notations together, please. Please find m sub pq for q at 4 f of 4. And so you notice here, if we're going to be figuring out what the slope is between these 2 points, I need to know the coordinates of both points. Well, I already have what the coordinates of P are. They're 2, 1. And I know that Q is at 4 comma something. Well, I have to find out what that something is. So figure out, what does f of 4 equal? So plug 4 in for x. What does f of 4 actually equal? And so then in this question, what it's really saying then, in all of this notation here, is it's saying find the slope between these 2 points. Okay. What is the slope between those 2 points? It's up 3, it's over 2, therefore yes, our slope there is 3 halves. So m sub pq in this case equals 3 halves. All right, having seen it, please now find this value of m sub pq. So first thing you do is you figure out what f of 1 actually equals. Well, that ends up equaling 0.25. So these are our 2 points. Now in this case, it might not be quite as obvious just looking at the graph, because I'm dealing with a fractional value down here, a decimal value. So we actually could do the calculations here, like we could do 1 minus 0.25 over 2 minus 1. That is, behind the scenes here, what we just did here is we did like the y2 minus y1, or the f minus the actual f values over the x values. And so when we do that, then we end up with 0.75 over 1, which is just 0.75, or 3/4 because it's a slope. Either way is fine there. All right, so in this problem, we're now taking a little bit of a different view, but we're actually going to be doing the same kind of stuff with this. We're still going to be dealing with some secant lines here. In this case, you can read this on your own if you want to. Basically, it says we got a cardiac monitor that's measuring heartbeats in a certain amount of time. And so we get this data out of that monitor. All right, so what we want to do is we want to figure out the secant line, the slope of the secant line specifically, at a number of different times. And notice we're looking for t equals 40 being the kind of the consistent piece of this. So that I'm going to do t equals 40, and then t equals 36. We want to find the slope between that. And so in order to do that then, I basically need to do my y2 minus y1 kind of a thing on the top because of the slope. That's going to be the difference in the heartbeat. So it's going to be the 40 2806 minus, remember in part A here we're doing t equals 36, so I go over there and I find that it's 2530. So minus 2530. And we put that over the x value, so that's going to be 40 minus 36. Do that calculation now. And yes, decimals will be okay. And when we do that work, we end up getting a final answer there of 69. Now, for that answer, that means 69 what? What would a units be on that number? Yeah, that would be like heartbeats per minute. And so notice that the slope of our secant line is also telling us a rate. It's telling us information about what's happening in this problem. Okay? Now, with that in mind, having seen how that one's done, please take a moment, figure out the answers for B, C, and D as well. So for those, check the rest of your answers now. So for B, 72.5, C, 71, and D was 68.5. All of those are heartbeats per minute here. Now, we found all those different secant values, but what we'd really like to know, because all those were based around this time being 40 minutes, we want to know exactly what was happening right at 40 minutes though. All of these values are what was happening between that value and 40. So what was happening exactly at 40? Well, we can't know exactly from the information we have, right? How can we estimate it? One option is find an average of all the slopes. Okay, what else could work? Yeah, the data seems to have kind of this weird look, right? It kind of goes up in the middle and then goes back down. So maybe just an average of the middle two, the closest two, that might be better. I suppose if we want to get really advanced, we could even look to see, okay, well, it seems like it's peaking here, but maybe it's actually like peaking between them, so it might actually be higher. You know, we might actually be seeing this sort of a thing going on with the graph, and we might be getting just these, and what we really want is what's going to happen right here. So we could actually plot the points and kind of do a best fit curve. Now that does sound like a bit more work, right? Let's just find an average then. What's the average of those middle two? Yeah, so, okay, that's a lot easier. We can find an average of those middle two. That gives us 71.75, because we add the 72.5 and the 71 divided by 2. And so that could give us a nice estimate. Those other methods could as well. But they're all just ways to kind of estimate the slope of the tangent line at t equals 40. What could we do to get an even better estimate, you know? If we weren't just restricted to this data, what else could we do?
39.
More numbers definitely would look like they would help. The most useful numbers would probably be, well, maybe like 39 and 41 I heard come up. Could we even get closer than that?
40.0001.
We could even get closer than that, right? The basic idea is that the closer we get, the better off it could be, although it could be kind of tricky with heartbeats per minute, right? So it could get, where the data being discrete like this, it might prove a little bit tricky, but yeah, the closer we get to it, it seems like the better our estimate is. We're going to be working now with this equation, this y equals cosine of pi x. The first thing that I want to do is I want to figure out what the coordinates are of p. And I'm given that this is what p equals. Going back to that notation I described at the start of class, right? So we know the x value must be 0.5. We want to figure out what y is, and of course y equals whatever cosine of pi x is. And so that's why in here you see cosine of pi times the x value, the 0.5. Now, I want to know what that value is, and I don't want to have to use my calculator for it. Can you still do that?
No.
Well, cosine of, well, okay, what's 0.5 is a fraction? 1/2, right? And 1/2 pi then is the same as pi over 2.
Oh, unit circle.
So, Yes, you do still need to know your unit circle. It's going to come back all year long.
You know what?
To help you with that, remember for unit circle stuff, visualizing that unit circle is a great way to go. And so if I want to know what cosine of pi over 2 is, I visualize the unit circle, then I visualize where pi over 2 is. Now pi over 2, that's a nice easy one, right? Remember, that is straight up. 90 degrees, basically. Cosine, the last thing we have to know then, is cosine how far we go over, or is cosine how far we go up? Over, yeah. So how far did we go over to get to that point? Well, to get to that point, which is straight up, we didn't go over at all. That's 0. And so P is the point 0.5, comma 0. Yes, you still have to know unit circle. Now, right below that, notice it says Q is the point x, comma cosine of pi x. Notice this is just a definition. There's no question there. It's just telling us that we are now defining Q to be any other point from that same function. Now, I laid all that stuff out first just so it'd be a little bit more when we do the actual problem with this one. And so we calculate our slope values here. And notice how we do that. For like that first one, we're going between P and Q, right? P is the point 0.5, comma 0. And for that first line, x is at 0, comma, then plug 0 in to figure out what x is. Cosine of 0 is 1. And so then to find the slope, we do 0 minus 1 over 0.5 minus 0, which gives me a negative 1 over 0.5, which equals negative 2. Repeat the process for each one, and we can get each of these different slopes. All right, and now that we have all that data, I want us to be able to use these results to estimate the slope of the tangent line. Because remember when we were looking at the heartbeat data, if we had more data that was closer to the actual value, we could estimate it better. In this case, we have a lot of numbers that are getting really close to that desired value of 0.5. And so, because I want to be as close as I can to this, well, we keep getting closer and closer to estimate. So, what would you estimate the slope of the tangent line would be here? Yeah, it seems like the number that we're getting really close to here in the middle, because we're looking to see what's happening right in here. It seems like that slope is getting closer and closer to pi. Now, with that in mind, we look to see would that be reasonable in this kind of a problem, and it's possible, yes, because notice this problem actually involves pi. It involves cosine, one of those trigonometric functions. And because of that, yeah, pi is more likely to come up. If this was a graph of like x squared, okay, pi would be very, very weird to show up. So, yeah, it kind of makes sense. So let's go ahead and go with that. Let's say that the slope of this function is pi. Oh yes, quite right. Negative pi, thank you. And so then if the slope is negative pi, please write the equation of the tangent line that goes through that point. So we already know y equals a negative pi x plus b. And so if you do this by plugging in a point for x and y, we can do that and then solve it. And you end up finding that b equals 0.5 pi, or pi over 2 if we want to make it look in something that's a little bit more familiar. But then with that, we can write our final equation. Our equation then would be y equals a negative pi x plus pi over 2. And yes, we would leave our answer in that form with the pi's and everything in there.
And we don't have a log.
All right, and so having figured out that equation, I just want to bring home what you really just did in another way as well. because I gave you an equation, y equals cosine of pi x, and let you do it for that. Graphically, this is what we really just did as well. So we took the point here at 0.50, and we found the slope of the tangent line to that. And remember, we found the slope of the tangent line was a negative pi, and then we found our y-intercept, which was pi over 2. And so we wrote the equation of that line and actually found out what it was. It turns out exactly, I know we're estimating, but I can tell you, yes, that is the exact amount and the exact equation of that tangent line. And we're able to get there by just getting closer and closer and closer to that actual value, remember.